Alright, so now we're going to talk about equilibrium. And before I start with equilibrium, I'm going to go back to rates. Okay, so remember in rates, you have some time and we're going to do a simple chemical equation. A goes to B. And recall that A is disappearing over time, so it's going to eventually hit 0. Okay, this is the amount. This is of A, and B is going to reach some amount and then stop forming. And B should stop forming because there's no more A, right? So A is gone, right? So these are full-headed arrow going to the right, okay? And so the picture, again, we'll just draw it for fun. Initially we have only A's, and then over time some B's get to be formed, and eventually all B's remain. Okay, this is a 1-to-1 ratio. Okay, so no more, only B remains, no more A, right? So this is as time progresses, T. Now in equilibrium situations, we draw it slightly different. A goes to be like this, and then look what happens. I draw a half-headed arrow going forward in the forward direction, okay, and a half-headed arrow going in the reverse direction. This is an equilibrium condition, a little bit different from the one I drew above, okay? In this case, what happens is this. This is one of the possibilities that can happen. We look at this graphically, and then we'll look at this visually and compare the two. And so, again, you start off with A, and as A starts to decrease, it doesn't really hit 0. Okay, there's still a little bit left. Alright, and so this is the amount of A. I'll just label A with letter A, okay? And then B starts to increase, and then once it gets to that point, no more A can turn, the amount of A is turning into B is no longer is affecting the amount of B increasing, okay? So B remains the same afterwards. In other words, so these are B's, this is the B curve. And so what I want to say next is let's draw the picture of how that looks like. So initially there are some A's, right? And then B's form. Alright, so only one B formed here, and then finally, as time progresses, we get this situation. We get one A and two B's. Alright, and the reaction is finished here. For this case up here, it's finished also, so done. Reaction is complete. Here, done also. Alright, so notice that there's still some A remaining. Okay, it didn't go all the way to the bottom, which would be 0 amount. This one does. Alright, so this is what equilibrium. So in an equilibrium reaction, you will have both reactants and products remaining. Okay, that's what's different about equilibrium. This is what we find. This is what happens in chemistry sometimes. Okay. So now we know. Usually we've done a lot of stoichiometry calculations like this. If we have this much A, how much B can form, and you can do those calculations, right? Here we don't do the math for this. Okay, we only learn the concepts. But you could, if in Chem 1, you would learn how to do the math for this. How much B is remaining, how much A is remaining. Alright, so I'm going to go erase this top one. In this case down here, notice that there are more B's than A's, okay? Because this is amount on the vertical, the amount of B being produced, and then the amount of A disappearing over time. Because there are more B's, we say that the reaction position, or the equilibrium position, it lies to the right side because there's more B's, okay? So we say that the equilibrium position lies to the right. The right meaning the right-hand side, the product side, okay? Product side. Okay? Because there's more B. Sometimes in equilibrium position though, might lie to the left side. So let's see how that might look. The graph would look a little bit like this. Again, amount here, T here, and you might get this situation. Alright, so you reach, I'm actually putting little dots on where they reach equilibrium, meaning the concentration or the amount of A and B no longer increases. Okay? So this is now A. Notice that in this situation there's more A than B, okay? Alright. So the picture looks a little bit different. Yeah, let's draw a visual to compare the two, okay? Okay, so the visual would be A. We start off with a lot of A, no B's, and then this is at equilibrium. Alright, so this is finished. Done. The reaction is complete. Now you have 2 A's and 1 B only. So there's more A's than B's is what I'm trying to say here. Down here is a little bit different. When it's done, there's more B's than A's. Okay, so up here, the equilibrium position lies to the left, which is the reactant side, right? So this is the equation. So equilibrium lies to left, or reactant side. Alright, so alright. Okay, now what we'll talk about is we do need to look at some calculations. They're not so bad though. Yeah, so let's take a look at that. Alright, so for equilibrium reactions, there is something called the equilibrium constant. Okay, it is K, okay, capital K, and there is an equilibrium equation, okay, so Eqb equation. The equilibrium equation would be K equals you multiply the products and you raise them to the corresponding coefficients in the balanced chemical equation, and then you divide that by the multiplication of the reactants raised to their corresponding coefficients in the balanced chemical equation. So let's assume A plus B is in equilibrium with CC plus DD. The lowercase letters here represent the coefficient, okay, in front of the chemical species, which are the capital letters, okay? So these are the coefficients. A, B, C, and D. The chemical species are the capital A and B. So these are the reactant chemical species on the left side. Reactant chemical species. And C and D are the product chemical species, because they're on the right side of this equilibrium arrows. Product chemical species. Right? And so if this is some generic equilibrium, then it would be the products multiplied by each other, their concentrations. Okay, remember the brackets indicate concentrations, which is an amount, usually moles per volume, okay? Times concentration of C times concentration of D, both of them raised to their corresponding coefficients, lowercase c and lowercase d, divided by the multiplication of the reactant concentration A multiplied by B raised to their corresponding coefficients, A, B. Okay? So this is some mathematical expression that you can calculate. Alright, and so let's take a look at an example, a real example. So let's just do N2 reacts with, these are gases, all of these are gases. And we do have to, we're going to assume that this is a, we've seen this equation before, let's assume this is an equilibrium reaction. We have to balance this, okay? So if we balance this as a 2, and then this is a 3, alright? And so we use this generalized equation, but notice that in this generalized equation there are 2 products and 2 reactants, right? Here we only have one product, so there is no other reactant to multiply, or no other product to multiply it together with. Okay, so that's the products, the concentration of NH3 raised to this 2 power, because the coefficient 2 there, right, goes there, divided by the reactants concentrations, N2, and times the concentration of H2, and that's cubed, okay, like that. And then, so this is the equilibrium constant and how you would calculate these. Now, I would have to give you these concentrations, okay? And these concentrations are at equilibrium, alright? So assume we mix some reactants together, and then we wait over time until this thing reaches equilibrium. That is, their concentrations don't change anymore. The products and the reactants concentration don't change anymore. But so let's just draw it for a visual. Let's assume there's some NH3s in here. And let's put like 4 NH3s in here. And let's just put some, there's an H2 down here and an N2 up here, okay? Let's assume that this is my equilibrium amounts, okay? We waited for equilibrium to get established, or to reach equilibrium. And so we can assume these are moles, okay? So we have moles here, moles here, moles here, moles here. For 4 moles of NH3. And we have 1 mole, I'll put that in a square, 1 mole of H2 and 1 mole of N2, okay? So 1 mole of N2 and 1 mole of H2. And these are moles though, and of course these brackets mean concentration, right? So quickly, concentration is equal to concentration C is equal to the amount of moles per unit volume, okay? And actually note how many moles, this is just a easy, simple idea. Assume that the volume that all of these gases are in, we're going to assume that they're all in 1 liter, okay? Okay, so now I can do this calculation. We're going to do the concentration of NH3. It's going to equal, let's count them, 1, 2, 3, 4 moles, right? 4 moles of NH3 divided by 1 liter, okay? 1 liter. So that's just 4 moles per liter, okay? So we have the concentration of NH3 now. We can do this for a nitrogen gas as well. From this idealized picture, we can see that there's only 1 N2 mole. So 1 mole divided by 1 liter. They are all inside of 1 liter volume. So then this is, the concentration of N2 is 1 mole per liter. And if we do this for H2, we can see that it's also 1 mole per liter. 1 mole per liter, okay? And so then we plug those concentration values into the equilibrium expression, okay? Or the equilibrium equation. So NH3 was 4 moles per liter. And we're going to square it, okay, because that's what the 2 means. Nitrogen is 1 mole per liter. 1 mole per liter. And hydrogen is also 1 mole per liter, and it's also cubed. 1 mole per liter cubed. So if you calculate this, it turns out to be 4 times 4, which is 16, okay? So the answer here is 16. The equilibrium constant for this situation is 16. This is the equilibrium equation, which you should be able to get from this balanced chemical equation. Given concentrations, you should be able to calculate an actual value, okay? Now, what you'll notice is that in this situation, you can see that there are a lot more products, right? Products are on the right side, right? Product, there's more NH3s, there's 4, right? Compared to the smaller amount of reactants. So we know that the equilibrium lies to the right. Eqb lies to the right. Remember that the right side is the product side, so that just means that there are more products than reactants. And remember, in equilibrium situations, you will have a mixture of reactants and products. So because of this idea, because of this equation, you know, the products are on top and the reactants are on bottom, we can come up with this. We can come up with this idea. When K is very large, okay, K is way, way bigger than 1, we know that the equilibrium position, the Eqb position, it lies to the right side. Lies to right. In other words, there's more products in the mixture. In the reactant and product mixture at equilibrium, there's more product. It lies to the right. And also, it's also true if K is very small relative to 1. Then the opposite is true. Equilibrium position lies to the left. Lies to the left. Lies to the left. That is, there's more react. In this case here, you can see that the K is 16. It is much larger than 1. It is a little bit larger than 1, meaning that there are more products in the reaction mixture, in the equilibrium mixture. So, just by knowing the size of K, you can know if the equilibrium position is on the left side or the right side. Yeah. Okay, in this situation, we had all gases, so you should include all of them. Okay? So this equilibrium constant K here, it sometimes works for most cases. Okay, so let me show you how they work. So in the case with the N2 gas reacting with the 3 hydrogen gas in equilibrium with the 2 NH3 gas, these are all gases. So you can do what we did earlier. Okay, when you have all gases, you can write the equilibrium equation like this. K equals a single product NH3 squared. There's no more product here, so I don't need to multiply it by anything else. Remember, if there's more products here, then you multiply it by another product raised to that corresponding coefficient. Here's N2 times H2 cubed. Okay, they're all gases. Okay, so this is a G, G, and G. So you can do this, no problem. Okay. The funny part, the hard part is it also works for aqueous things that are in equilibrium in aqueous solution. So let's say we have this situation: A aqueous plus B aqueous. Let's put a coefficient here. Goes to C aqueous plus D aqueous. Alright, and let's put a coefficient here. So if I told you to write the equilibrium equation for this equilibrium reaction, then what you could do is you can say, okay, I have the products multiplied by each other, C times D, okay, raised to the corresponding coefficient, so 2 is for C, and then there's a 1 in front of the D, we can put a 1 there, divided by the product or the multiplication of A and B, the reactants, raised to their corresponding coefficient. A has a 2 here, so we have to put a 2 here, and B has a 1 here, so we put a 1 here. So these are all aqueous, so we can do this also, no problem. Okay? So this is my equilibrium equation, okay? And again, if I gave you these concentrations, then you can plug them in and then calculate this, if you're asked to. Alright. Now, what if this happens though? What if it's aqueous, and then this is a liquid? In this case here, if it's a liquid, then you do not include it. Okay, that's the rule. Okay, now equals just C. Only aqueous chemical species can be used in this equation. I'm going to leave the aqueous out to make it easier. So this is the correct answer for the equilibrium equation. Again, the D is now left out because it's liquid, okay? So it becomes more important, these physical states become important. If they're all gases, then you can put them in. They have to all be gases though, okay? They have to all be gases, then you can use all of them. In this case here, since we are in an aqueous solution, if you make a liquid, that does not go in here, okay? Likewise, if they are all aqueous, and let's say this is aqueous, and let's say you find one that is a solid, because precipitations can happen, right? So this one's a solid. Now, if it's a solid, you can't use it either. You only can use aqueous. So in this case here, it's just D. Concentration of D raised to 1 power divided by the concentration of A raised to 2 power times B. Alright, and B is also to the 1 power. Alright, so this would be the equilibrium constant calculation for this equation up here. So notice here that I do not include the solid, I only include aqueous. Okay? Alright. Only aqueous goes into these equations. Alright, so now we've learned about what an equilibrium reaction is. Remember, in an equilibrium reaction, you will have a final mixture of both reactants and products. Okay? We don't need to calculate them like we did for regular reactions. And then sometimes there are more products, so that means that the equilibrium position lies to the right side or the product side. And sometimes an equilibrium mixture might lie to the left-hand side or on the reactant side. It just means that there are more reactants than products. We also looked at an equilibrium constant that can also tell us if the reaction lies to the left or the right. If K is much larger than 1, then the equilibrium position lies to the right. If it is much less than 1, it's likely to lie much to the left side. Alright, let's stop that there. Okay, so I need to also talk a little bit about rates, okay? Rates, how fast an equilibrium is happening, okay? And so again, we're going to take this simple idea, A in equilibrium with B, okay? So this reaction, okay? But initially, I'm going to try my best to show you how it's happening, okay? So first, there's only an amount of A, okay? And it's turning into B quickly, okay? Alright, so I'm trying to show you that the size of this arrow is telling me how fast A is turning into B, okay? Initially, you don't have any B, okay? So then A is turning into B super fast, okay? But as B forms, it starts to return to become A a little bit. And that's because the arrow here I'm drawing is a little bit smaller, right? Small meaning that it's how much B is turning into A over time, okay? So this arrow here, it's telling me how fast, the size of this arrow is telling me how fast A is turning into B. No B is turning into A because no B has been made yet, okay? Finally, some B has been made in this second situation here. And then as B is made, it's slowly turning into A. And that slowness is represented by this smaller arrow. Notice that the A turning into B is still quite large, meaning the rate of A turning into B is still quite large. And we can call this F for the forward rate, and we can call this R for the reverse rate, okay? And then over time, what happens is, notice that the reverse rate is getting larger, okay? And the forward rate is getting a little bit smaller, okay? Eventually, the forward rate equals the reverse rate. Now, I am not telling you how much A and B there is, I am telling you about their rate, okay? How fast A is turning into B. Initially, it's very fast. And then it slows down, and slows down, and slows down. As B starts to form, it starts to increase its rate to become A. Eventually, they both reach the same rate. So every time A turns into B, one B turns into A. That's here, okay? The rates are equal. A is turning into B as fast as B is turning into A. In these other situations, they are at non-equilibrium position. This is equilibrium. It has reached equilibrium. The forward rate equals the reverse rate. Okay? That's why they're the same size. Graphically, if we look at time, okay, because actually, in this case here, going down is time. Okay? Time. So initially, is 0 time, right? 0 seconds. And then as time goes on, you get this situation. Alright, and then the size of the arrows represents the rate. So if we write rate on the vertical here, the rate, we can say the rate of A turning into B, okay, is high at first, right? It's a high rate because that arrow is so large, okay? It's the forward rate. It eventually will reach some amount, and then they will eventually equal, okay? So this is the forward rate, and this is the reverse rate. The reverse rate is starting to increase, and then eventually they reach the same amount. Okay? So the forward rate decreases, and the reverse rate increases until they are the same rate. Hence, the same size arrows here. And so this position is equilibrium. And that is the definition of equilibrium, okay? When the forward rate equals the reverse rate. Okay, so that's just a more in-depth look at equilibrium, alright?